These really tiny doses of opioids release a small burst of free radicals that then ultimately lead to this amazingly adaptive protective potential in the heart. And it mimics what would happen when you do these mini micro heart attacks. It turns out that when you do these mini micro heart attacks, the heart releases a small amount of opioid, which then feeds back onto itself to cause this protected state.
Dr. Hemal Patel is a unique scientist with all the bona fides you'd want from a researcher, but with more openness. He has spent time digging into meditation, not just as a health practice for himself, but also publishing studies on meditation and on a research idea he calls really a quantum study, which is a quest to analyze thousands of humans while meditating. This while driving his career to be a vice chair for research in the Department of Anesthesiology at the University of California, San Diego School of Medicine, and a career research scientist at the VA, that's the Veterans Administration, and the chief scientific officer for Versea Discovery.
Anything you look at is a mitochondrial stressor, but if you take it in a small dose, it creates this huge resiliency phenotype. The other thing that I think you can't replicate in this biohacking world is...
Hi, my name is Chris Burris. I'm a longevity expert and the chief scientist at a lab focused on a longevity molecule. My primary focus is to help people live longer and better lives with science. Make sure to subscribe and share so you and your friends can live longer and better, so you and your friends can live beyond the norms.
Hi, and welcome to the next talk on the Live Beyond the Norms Health and Longevity podcast. I met this next speaker, Dr. Hemal Patel, at the Biohacking Expo in Miami this last February. I was at his booth, mescreen, and purchased his complete mescreen package. We started talking, and it became obvious to me that we should continue our conversation. We geeked out on mitochondria, and we have a mutual acquaintance at the University of California, San Diego. At the end of the conversation, we plan to review my data, from mescreen, which is about mitochondrial health, from that complete screen on my podcast, and, well, here we are. Just for some background, Dr. Patel is a unique scientist with all the bona fides you'd want from a researcher, but with more, I'm going to say, openness. I don't know exactly how to describe it, kind of an openness that I'm not used to. He has spent time digging into meditation, not just as a health practice for himself, but also publishing studies on meditation and on a research idea he calls really a quantum study, which is a quest to analyze thousands of humans while meditating. This while driving his career to be a vice chair for research in the Department of Anesthesiology at the University of California, San Diego School of Medicine, and a career research scientist at the VA, that's the Veterans Administration, and the chief scientific officer for Versea Discovery. We are here today to talk about mitochondria and my mitochondrial health scan. Dr. Patel, thank you so much for joining us today.
Yeah, great to see you again, Chris.
So and as I mentioned already, there are so many directions that this could go. I'm really going to have to reel myself in and try and stay focused. Before we really jump in, what in your background pushed you to be a research scientist and then have the balance of systematically studying meditation while simultaneously putting together a mitochondrial test from blood samples? Like what makes Dr. Patel?
Yeah. As of growing up in an Asian Indian home, you have two choices. You either become a doctor or a lawyer, and you have to become the right kind of doctor, which is the MD, not the PhD. And so that was sort of the path that was laid out in front of me. I was really into science, but explored both ends. So in college, I double majored. I was a biology major to start off with. I went to a liberal arts school where you had to dabble in other areas. And I took an intro to philosophy class, and then fell in love with it and actually double majored in philosophy, religion, as well as biology. So I had both those paths open to me. Most of the philosophy, religion majors who studied a lot of logic became lawyers, and the biology guys went into med school or grad school to do whatever they wanted to do. Very early in my college career, I started working in a laboratory, and I came to this notion that maybe medicine wasn't where my best efforts were, what I could do the most impact to the world. And it was really the discovery phase, the creativity thing that I was sort of into, right? And that, I think, goes with the philosophy of religion as well. So I chose this path of becoming a PhD scientist, and this was difficult for my parents to swallow. This notion of, well, what is a PhD? I mean, they had no concept of what this is. And of all things, I chose to become a PhD in pharmacology and toxicology. And so the first comment was, well, are you going to work at Walgreens? And so, again, no concept of what that means, right? And so I really sort of focused on this idea of, can I understand how drugs work in a human body? And can we design better and more targeted therapeutics to solve the problems of human health? The PhD work that I did focused on looking at ways to protect the heart from a heart attack. And are there mechanisms that could be endogenously induced? And then could we find drugs that do the same thing without you having to do this? So we discovered that if you actually give the heart a tiny little heart attack before you give it the big heart attack, it remembers and learns from that and is completely adapted. This process happens in virtually every organ, and there's a whole sort of downstream signaling mechanism that's launched that does this. Turns out the key feature of this is mitochondrial stabilization. And so this is where I really got interested in mitochondria. And since I was in grad school I graduated in 2002, since then, this has been the focus of a lot of the research I've done. As we've started exploring more and more about mitochondria, it turns out that they become sort of this real conduit for how we live and survive. There are these tiny organisms that got incorporated into more complicated cells billions of years ago, and there's a symbiosis, and they provide not only energy, but they've created this primacy role in cells where they're gatekeepers of cell death and survival. Most people think of them as these powerhouses, but I think the more important concept is this gatekeeper function, right? And so we've been looking at both elements of this and really thinking about it from a large perspective. About 4 years ago, I went down a different path. For 20 years, my lab has been focused on proteins and figuring out how these proteins work at the molecular level and how we could therapeutically target these for various diseases, which is a long road path to endpoint therapeutics, right? And it took 20 years to get to the point where we discovered a protein. It does really cool stuff. We were able to take that really cool stuff, make a patent out of it, and we're close to coming up with a cure for ALS, which is great. But it takes 20 years to do this. About 4 years ago, I got put into this field where we started thinking about other ways to change health, and could the mind and the way we think and how we behave and what we do personality-wise change our body. And so now, instead of taking a drug from an external source, could you create a new pharmacology based on how you think, right? And meditation is one of these extreme ways to do this. And so we started working with this amazing individual, Joe Dispenza, who does events all over the world. And he just gave us this ability to go into his events and just start playing around and in a very unbiased way, start to look at that process and see if the mind connects to the body and if it can change the body in unique conceptual kinds of ways. Again, everything in my life happens for a reason. The way I got into that work is I shared an office for about 10 years with a pain physician, an MD PhD, Toby Muller-Bertram. Toby and I, the goal of this was to share an office was for the PhD to rub off on the MD and the MD to rub off on the PhD. We never worked together, but we became really good friends. And so then he left the university, started a pain clinic in the Palm Desert area, and then really was managing the opioid crisis in his clinic, right? The easy thing to do with pain management was to write a script for opioids, have your patients start taking this, and ultimately lots of people became addicted. And so this was not the path forward to managing pain. So he built an integrative pain clinic where he started experimenting with alternative approaches, and meditation was one of them, did acupuncture, all kinds of things. And so he went to a Joe Dispenza event because one of the practitioners in his clinic was a Joe person, and he was blown away. And of course, he went up to Joe and said, "We need to study this." And Toby's like, "I know a guy." And so I'm the guy. And so that's how we got sort of circled into this. But it's been completely amazing to go full circle around just basic biology and then really going to human biology at the end of the day and looking at it from the perspective of how we balance our personalities and ultimately how that really relates to how we balance our energy. I think that's the key feature to disease management.
Wow. Okay, so there's a lot. When you started studying philosophy, I took a philosophy course. You studied mechanical engineering, and I was extremely nervous about philosophy because it's falls under the moniker of liberal arts. But I got in there, and there was nothing more logical than like it fit in with all of my training up to that point. I really found that, I don't know, why is it in liberal arts if it's so logical? And what a fantastic concept of putting, biology and philosophy with this little, get that liberal arts spin in there so that there's a lot more creativity. Really all the creative ideas. I'll never forget the talk I went to. I got to see Dr. Linus Pauling speak. And he, a two-time Nobel Prize winner. One of them was the Nobel Peace Prize. And one of the things that resonated with me, and he was talking about all the things that he accomplished, they were when he blended chemistry with biology, two things that he had PhDs in, that he made the most impact. And, now there's a biochemical that didn't exist when he was then. And so anytime you're kind of cross-blending these things, just some amazing things can happen. My dad died. I'm very interested in your research. My dad died with ALS. So did his mother. And so I actually need to take the genetic test. In my book, I talk about how the first ALS meeting that I went to with my dad and his doctor, she was like, you should get tested. By the way, 2 years ago, I would have said, don't bother because there's nothing we can do. And now there's so much dramatic changes happening. Whether it's on a genetic level, you're talking about a protein level, like there are things that are actually might be applicable. So you should understand your risks. I haven't done that yet. I just need to get around to it. So doing some amazing stuff. When we got together, you mentioned, I think it was the NASA twin study, right? So they stuck one genetically identical twin up into space, and they've done all this kind of analysis on them and what are the differences. They came to you, so NASA came to you and said, hey, we want to know, did they want specifically mitochondrial, or did they just want like, hey, what can you tell us? And talk about them approaching you and your initial response, right? Because my understanding, and maybe talk a little bit about how you assess mitochondria prior to what you're doing now with mescreen.
Mescreen, yeah. So the NASA twin study was a multi-institution study, right? So they involved 10 institutions across the U.S. They handpicked them for the unique abilities they had. UCSD was one of these sites. And again, serendipity, right? So the person that was the lead PI on campus, she and I had known each other for a long time, and she knew the capabilities of the lab. And so one of the things that NASA was aware of is that, and they've done lots of animal studies where you send animals up into space and you look at functionality, is the mitochondria are impacted. And it's like a no-brainer, right? The mitochondria should be impacted. They're in every one of our cells except for our red blood cells, and they control energetic profiles. And we need energy to survive. And when you're put into an environment where you're not adapted, your energy systems are taxed and they go in the wonky wrong direction. And so one of the things that on Earth we've never had to adapt to is zero microgravity, right? Our bodies haven't had to deal with that. When you go up into space, your heart doesn't have to work anymore, right? It works because there's gravity on ground. And so it literally stops behaving the way it normally should. And you get this pooling of blood in your head. And so if you look at pictures of astronauts, you can Google this, look at an astronaut on ground versus space. Their face balloons. I mean, it like doubles in size because all of that blood is pooling there. And so this creates a lot of pressure, a lot of stress in the system, and your mitochondria are taxed to the maximal level. The question was, how do we test this, right? NASA said we can't give you access to any tissues, which is how we would want to do it. The gold standard for looking at mitochondrial function that we do on campus all the time as part of research studies is you come in, we numb your leg up and with a local anesthetic, and then there's this gigantic needle that gets bored into there. You pull it out, and some
By the way, if
muscle.
you're just listening, he made like a thrusting as if you were stabbing somebody with a knife, which is probably what happens.
I mean, maybe it's not that graphic, but it's at that level, right? That's what your mind sees when you see this needle coming at your leg. And then when you pull it out, pieces of tissue come out, and then we get that tissue in our lab, and then we spend the next 6 to 8 hours analyzing the mitochondrial function in that tissue. You can see how space would make that difficult, right? Elon Musk has solved a lot of problems, but he hasn't figured out how to get samples from space to ground in 20 minutes where we could do these assays
Mm.
firsthand. So the thing we had access to was blood. The concept was blood contains a lot of factors, and could we use that as a surrogate to then do a version of this mitochondrial testing? And so we were like, all right, let me think about it. And so I came up with this idea that if the blood is a capture of your exposed environment, so your unique genetics, so whatever your cells have, whatever your mitochondria have, they create a biochemistry in your cell, right? This mixing of biology and chemistry and all these factors that get released. So when you're exposed to a stress environment, all these systems get taxed, your nucleus, your mitochondria, all the stuff, bags of cells, and then every one of your cells are responding to that environment. What they do is then they secrete metabolites, your gut's secreting stuff, you have exosomes floating around. This all gets captured in your blood. And so the idea was if we have that as a unique capture of you at a specific time window, we could transfer that environment to a living cell that represents different organs, and we could then see how your mitochondria are changing by looking at this surrogate measure, right? Your environment onto this cell to see how that cell's behaviors change from a mitochondrial perspective. It turned out that we were able to predict some dysfunction that the astronaut would have based on this plasma adaptive transfer experiment. And so then we were off to the races, right? So now this gives us a conduit to start applying this to human conditions. Space gives you this extreme stents, but now we could do this at scale, right? You don't have to go into a physician. You don't have to get this needle muscle biopsy. We just take your blood and give you some assessments of your mitochondrial functionality. And so this is where mescreen really was born and took off. One of the barriers that still existed was that with the current tests we developed with NASA is you'd have to get a blood draw, right? You'd have to go to LabCorp or someplace, hopefully not the space station, but somewhere on Earth, get a blood draw. That blood would be after processed in a unique kind of way and sent to us in a frozen or an ice pack situation, so you preserve all the material in there. That creates barriers. It's doable and scalable, but create some financial and sort of shipping and other logistical barriers. So we came up with was this blood card technology, right? It's a bilayer system. You drop a couple drops of blood on this. It separates out your serum. The sample dries, gets put into a desiccated pouch, and comes to our facility. You can store this, we've shown up to 2 months at room temperature, and the sample looks as if it would if we'd just freshly gotten it minutes after you isolated and isolated that serum sample. And so now we can run the exact same assays we developed with this NASA program, but off of this card. This gives us ability to basically get samples from anywhere in the world, and we're doing some crazy studies all over the world with this in different sort of extreme situations and how we could look at factors like this. We're doing studies with people who are doing different, plant-based rituals in different countries. We're looking at unique disease processes in countries where they don't have the correct molecular systems to look at stuff. But now with this preservation on this card, we can get the samples to the US, do our extractions and look at unique elements. We're looking at a place in town where, it's called Air Locker, and you can literally go from sea level, which is what San Diego's at, to 12,000 feet elevation in 2 seconds because they scrub this room of oxygen and they can set the elevation of whatever you want. And we're starting to look to see what happens when the human body adapts to these unique sort of situations. So it gives you this huge flexibility. And now it gives the ability for this card to be sent to your grandma who's living in nowhere, USA, that can literally give us a sample and she could figure out what her mitochondrial functionality is, and then give you some insights into how to change the behavior of your mitochondria to live a much healthier life. And this is what I think mescreen and Versailles Discovery is about, is the next phase of how to evolve human health based on energetics.
So there's a lot. I want to talk about the card technology, but first, you're jabbing the muscle, and I love the gesture that you had because I think that is what we felt. At one point, I went to a orthopedic surgeon, and I had some muscle problems, and he was like, "We're going to do a muscle compartment disorder test." And I was like, "Well, what does that look like?" We throw you on a treadmill, we jab a needle into your muscle and we take a pressure reading. And I was like, well, we're not going to do that. Like, that doesn't sound pleasant. I think I'll be all right. So I still, my muscles tend to tighten up a lot, and I may have this muscle compartment pressure disorder, but I'd rather experience that than the jabbing.
Yeah.
But so you collect this sample. What are you really looking at, right? So you got the tissue. You're like centrifuging, I'm assuming, some sort of process down to the mitochondria, and then you're assessing like what about the mitochondria are you able to kind of discern?
Yeah, so I mean that the tissue is literally the gold standard, right? So we have your genetics, your mitochondria, and we look at it in real time and space. So when we get that tissue, we tease the fibers of your muscle apart. It goes into this really sophisticated system that then measures oxygen, right? It's the flux of oxygen that we're measuring. And your mitochondria consume oxygen as they're making energy, as they're making free radicals, and all these other things. And so we know from biochemistry that there's certain substrates that drive different complexes that sit in your mitochondria. So the holy grail of mitochondrial energetics is there's this electron transport chain. Mm-hmm. So it's transporting electrons up this gradient, and as it's transporting electrons, the mitochondria has this unique multi-layer membrane system. There's an outer membrane, an inner membrane, which then creates this inner membrane space, as well as a matrix. And so what happens in this process as electrons are moving is you're pumping hydrogen out of the matrix into this inner membrane space at every sort of turn of this electron transport. The final component of the electron transport chain, the ATPase, which is going to take ADP to make ATP, uses that gradient to shove hydrogen back into the matrix. And as the hydrogen comes back in, it basically is like this fan motor that turns. And when it turns, it gets to add a high energy phosphate to ADP and makes ATP. And this is a very efficient way to make energy, right? And this is why they've survived so long in our cells, is they give us this efficiency phenotype. There are other systems that our cells have adapted. So glycolysis is the other way to do this. But the payoff for glycolysis versus mitochondria is night and day in terms of how much energy you get out of mitochondria. And so mitochondria really fuel adaptation and growth and resiliency because it's so much energy they're generating at the cost that you're creating. In a perfect system, the end result is a ton of energy and water, right? Mm-hmm. In a mismatched disease system, what you're making is very little energy, and you're making a lot of free radicals, these reactive oxygen species, because things aren't coupled. And so we can look at the coupling of your electron complexes with this muscle testing, right? So we can see how electrons are moving from one complex to another, and whether they're doing this in an efficient state. We essentially feed different substrates into the system, and we see how different complexes then increase or decrease oxygen consumption. And so this gives you a huge sort of look at different kinds of states of mitochondrial biology. The other thing you can do with muscle biopsies is you can feed different substrates into the system. So you can feed the muscle glucose, and you can see how glucose is working in terms of breakdown products to create mitochondrial energy. You can feed the system fat, and you can see how fat is changing this. And you can feed the system ketones and amino acids and all kinds of things to see how energy is being generated in this process. So the muscle really gives you this, your genetics, your mitochondria, and how this is churning and moving. So it's a direct measurement of you, which I think is a great way to look at it.
And okay, so thank you. And then now we're saying, like, this is really a fascinating strategy. I don't know that it was obvious to come up with it. It doesn't seem like it would be obvious, which is to say, we've got the blood, and the blood is highly impacted by the mitochondrial processes of the cells that are around it. So let's take this blood and put it around some, we'll call them generic cells, or you can even specialize those cells. And the way that those cells react based on the surrounding blood indicates how the cells were reacting from where the blood was drawn. Like, this is pretty cool stuff, right? Where did that idea come from? Is there like, and by the way, I saw a video of you on talking about, and we spoke briefly about kind of water energy. This seems like that understanding of the energy in water, right,
Yeah.
fits this. It's like if that water has this energy and then can have this impact, then I've got this thing, and when I put it around generic cells, it should have this impact.
Yeah.
Talk about that a little, please.
Yeah, so I mean, we've been doing testing around this, right? So rodents are an easy model system to do this in. Humans are a little more difficult, but we're trying to do this and sort of recapitulate this in humans as well. So you can take a muscle from a mouse and test it on the same sort of assays that we're running with the mescreen cards. And then you can take blood from that same mouse and put it on the mescreen and compare the two, right? And so when we compare the muscle metabolism to the blood metabolism, there's almost a 1-to-1 correlation. So this suggests that there's something we're capturing in the blood that we put onto a muscle cell that gives you the same readout as if you're just going to look at the muscle itself. So why go through the pain of the needle and all this stuff when we could just look at blood, which is way easier to sample? So the concept behind the blood, I think, goes into what everyone's talking about right now in every space you think about, right? This epigenetic modification. So epigenetics is where your genes are modified by the environment through methylation events, microRNAs, histone modulations, all these things that then sit on top of your genetics, which is what epigenetic means, to modulate how those genes ultimately express. And so if we're thinking about it from an external environment, you create an internal environment. This internal environment has metabolites, it has exosomes, it's got proteins. All of this stuff is floating around, and it's sitting in everyone. All of your cells are being bathed in this one way or another. And if they're not, you're not living, right? The reason why you live is because those cells get oxygen, nutrients, and all these other things. That comes from circulation. It comes from your blood. And so the hypothesis is then that really is your internal environment. Can we now capture your internal environment at a specific point in your life, transfer this to a living system that's never seen that environment, and see how that system now adapts, and as a surrogate marker of who and what you are, right? And so this is what we're doing with this assay, is now your metabolites, your exosomes, your proteins, your hormone, whatever's sitting in that milieu that we've captured on this card gets put onto the cell, and that cell now has to respond to it. It's creating epigenetic changes at the nuclear level, at the mitochondrial level. It's got a mix of metabolites, and we're agnostic to that, right? We don't care about what metabolite is up or down. We're looking at the combination of all of these things that are creating the unique you that then change the behavior of the cell. This is why I think this has been so powerful. So we've been talking to a lot of people. We've done hundreds of these tests now. And we'll have these consultation sessions where we'll talk about the results and what they mean and sort of, go into insights. And what we're seeing is that a lot of people will feel not right? And they don't know, we don't know what's wrong with us, right? But we just don't feel normal. So they'll run a microbiome test, they'll run biomarker tests, they'll run hormone tests, they'll do this, that, and the other. And they're looking at a biased set of things that they're interested in. Maybe not the gut, but at least these biomarkers that you would run in a test, right? You're looking at hormone levels for testosterone or cholesterol levels or some of these things. And none of those tests come out to say that there's something wrong with you. For a lot of people that have these, what they call these psychosomatic kinds of things, they think it's all in your head, right? You're making this up. But they're convinced that they're not making this up. And a great example of this is long COVID, Lyme disease, and all these other things. You go to your physician, you're like, yeah, you're just making it up. It's all in your head. And these tests come out negative. So they confirm the physician's response that this is all in your head. What we're seeing when they run their mescreen is like, oh my God, I finally have a test that validates how I feel, because they look absolutely horrible on the mescreen. Because we're looking at the core feature of what disease should look at, your energetics. How are you making, moving, and using energy? This is something that most tests don't consider. Making, moving, and utilizing energy is a key feature of every process in your body. So why not use that as the underpinning of your baseline health? I think this is something that everyone should have, right? A mescreen score really at a basal state should be something that everyone could think about, right? It gives you your metabolic state. And if it's off, it gives you ways to move it to the next level, I think.
I love all of that. There's a lot of creativity that kind of went into this process. I don't have the background to go like, oh yeah, they do that in other areas of biochemistry all the time. Like maybe that is true. It just sounds like a really smart adaptation. And then I want to talk, because you did talk quite a bit about the kind of the storage process and the cards. Is that something that you and the team invented? Is that something that some people were using and you kind of grabbed onto and said, hey, this is how we need to accomplish this? What's the story about the card?
Card technology is not new, so these cards exist. There's other companies. They may not use the bilayer system that we're using, but there's other companies that are using blood spot kinds of things. And you can get, this is this idea, right? You can get a lot of information from blood. There's a company which shall remain nameless right now that raised close to $1 billion around this. It went south, but this idea that a drop of blood contains all this information, right? I've been saying we're 6 drops better than that company.
I remember you saying that, yeah.
And so there is this notion that there is a huge amount of information that our blood contains that we're not really thinking about. And I've been thinking about it from a unique perspective. So I lost my mother when she was 60, all of a sudden, and she was a type 2 diabetic, and she had a heart attack in her sleep, and she was gone. And so as a scientist that works in those areas, it was something that really sort of gnawed at me, this idea that I couldn't do anything to help her, right? And one of the things, and this is where the openness of where my mind goes and all the things we're into, I'll study anything if there's a component to this. And I think the philosophy of religion comes into this. There's a faith-based aspect to belief in science and other things. I come up with crazy things in my brain that no one believes, but I have this notion that there is some reality to it. I just haven't invented the right experiment to get to that state. Mm-hmm. And so one of the things that I thought about deeply after she passed away was this notion that we've been thinking about disease in the wrong way, right? If we want to solve diabetes, why do we keep looking at diabetics, right? The solution to diabetes is looking at that person who physiologically and morphometrically looks like they should be a diabetic, but they're not. So there's the answer to diabetes, is that morbidly obese individual that can handle glucose at a very high level. And so jokingly, we've said we're doing, I don't know what the population of the Earth is right now, close to 10 billion people. We're doing 10 billion experiments a day, 24/7, yet we're not harnessing any of that knowledge that comes out of those individuals. And it's in their blood, right? The solution to every disease is in the blood. And if we can mine it in a unique way in different stress situations and how people adapt to those stressors, I think we're going to get to the point where we can solve every problem that humans sort of deal with. And this is where mescreen comes out, right? That this idea of this environmental capture of who you are at the blood level can solve a lot of these problems, ultimately.
Hey, super quick break from the podcast. Hopefully you're loving it. This is a way you can support the podcast and take advantage of a great offer. We're offering 50% off of one of our MCT bottles. MCT is an amazing oil. Add the ESS60 molecule to it. It's even more amazing. All you got to do is leave a review on iTunes, send us a notification that you've left that review. We'll get you a coupon code that'll get you 50% off of our MCT oil and free shipping. Back to the podcast.
I've got a bunch more questions about mitochondria, and we may come back to them. I think it's probably a good idea. Let's jump into my test results, and we can kind of assess this real time. Let me share the screen here.
Yeah, so we're revamping the report. So the next iteration that we're beta testing right now internally is going to look way different than this and cleaner. We're eliminating a lot of the words, but we initially, as a scientist, I like words. I like to see things. Right.
I know. Isn't it painful? Because I'm with you. Like, I want the words, and then you got to, if you're going to make it for the masses, it's got to have less words.
Yeah. So we've revamped this significantly. So we'll go to the results themselves. So the first part of this test looks at your mitochondrial stress response. So now we have you from the card that we've reanimated in our system. And
just to give the audience a little background, I was at this conference. We did a finger prick, which I don't like finger pricks. I don't know. They're not that painful, but they're just irritating. And I usually have a hard time getting blood out. I was fortunate on this particular case. I got lots of blood. It goes on a card. It kind of runs like a chromatography thing up the card. And then that got, you guys managed it. It let it dried and then got it shipped. And then I got these results.
Yeah. So we basically punch out the serum, we reanimate that serum, and so that now is you in our system, right? And so now we transfer you onto this muscle cell, and we look to see what the mitochondria are doing. So the first result at the top is your baseline respiration, right? Respiration is how you're moving oxygen through that system, how you're respiring. So the baseline is an important number. So what we would want to see with the baseline respiration is you hitting basically the middle, 50% average. And so this is a normalized scale. It goes from 0 to 100. So all the numbers you'll see are on this normalized scale in this system. So a 36 is a low baseline number. So what this suggests to me is that there's something in your environment, in your blood environment, that suppresses mitochondrial function, right? We would expect that nothing should happen. It should stay at a 50 if it's average, but there's something that's lowering that mitochondrial respiratory rate. So this could be an indicator that we may want to think about this, right? And so one of the other things we're learning from this, and as we're educating people, is that you can't fixate on just one number in this test. You have to look at the whole test, the complete panel, in totality to make a decision about how to sort of move forward with health and life choices rather than just focus on that. So we'll keep that in mind, right? Your baseline number is lower than it should be. And so that
now just for clarity, so we're 0 to 100. When we say a 50 is baseline, is that just like a bell curve around the data that we have, or have we defined 100 is like optimized respiration for, you know, a theoretical optimization, or is that a bell curve around data that we've collected?
So baseline respiration, if it goes too high or too low, there's a problem, right? And this is why we have the reds on the two extremes.
Yep.
For a lot of these values, it's great to be average, right? People don't like to be average, but on this test, being average is actually quite good.
Yep.
And so our normative data group has elite athletes, people who are doing amazing longevity programs, people who are just normal Joe Schmoes off the street, weekend warrior kinds of things in terms of health, and then really sick individuals. And so we're looking at the full extreme to create our normative data set.
Okay. Yep.
And so this pegs you against that. So
so it's not, sorry to interrupt. So it's not just a bell curve. It's like, hey, we understand these people are in less health, so we're going to put them, whatever their numbers are, we're going to tag those as not being healthy. And the reverse is if they're really healthy, then we're going to tag them.
Right.
Do you bump, sorry that my brain just goes, or do you bump into elite ultra athletes? And would you tend to put them in a red zone, whether it's high or low, just because I think it's fair to say they're doing immense amount of damage to their bodies regularly?
I don't. It depends, right? And as the test results evolve, we'll talk about some elements of that. That there are things that potentially in the high extreme that are good and bad depending on what other elements of the test look like, right?
Okay.
So your baseline is a little bit low. So then what we do is now we start stressing the mitochondria. So one of the first stressors we apply is we stop the ATPase. So we stop the engine from making ATP. When this is blocked, you should have no oxygen flow through that system because the system is constantly measuring oxygen in that basal well, right? And so if oxygen is still moving through that system, that would suggest that you have an inefficiency, a leak state. And so this is what this efficiency marker is really looking at. And so your efficiency is average across the normative group. So that's good. So your mitochondria seem like they're well coupled. When they're supposed to stop, they stop, right? So that's a good thing. The next thing we look at is we stress the system to go as fast as it can. So we uncouple it and we make it churn as much oxygen through that system as it's sort of functionally can allow. Your mitochondrial potential then is looking at your baseline compared to where that churning comes out to, and it's average, so that's not bad. We see in elite athletes that are well coupled that mitochondrial potential starts to touch the 80, 90, 100 range, right? So they have this huge reserve capacity that we see. In people that we've seen in our database, so we ask people to do surveys so we get a capture of sort of what they're dealing with functionally and sort of disease status wise. We see some unique patterns that emerge. So people who have long COVID, we've seen some issues where they may have a lower mitochondrial potential, right? They don't have that reserve capacity. So they're able to survive, but then when their system is asked to create energy when they're stressed, there isn't a capacity to do this. So you have sort of an average capacity to do that. The mitochondrial index we're converting into an overall mitochondrial score, but basically it's an algorithm we're developing that looks at a variety of values and then things we don't report out as well that feed into that algorithm that give you a score. And so yours is on the slightly lower to average range because of that baseline respiration that's sort of in that lowish range and that decreased sort of overall potential that we see. So that's in a nutshell the stress test. So the second panel, then the second tier that we do, goes on to looking at energy profiles. And so we look in a basal state, whether you're making energy, if your system is preferring to make energy with glycolysis. And so is it using a glycolytic state to make energy? And then this is a wonky a bug in our system. So it should be aerobic, not anaerobic respiration.
Oh, yeah.
And so we fixed that, and I think I sent you the report before we fixed it. But basically,
okay, yeah.
So
and it's correct here, right? Just incorrect there.
Yeah, right.
Yeah.
And this is working with these guys who just, anyways.
Yeah. Copy paste, except
right?
not copy.
Yeah. And so that then looks at your mitochondria. Are you using glycolysis versus mitochondria? So glycolytic versus aerobic score. And then the Q score and the E score tell us whether you're using glycolysis and mitochondria in an efficient kind of way. So typically what we would want is your Q score to track with your glycolytic score. So because your Q score is sitting in the high range, that suggests that glycolysis is not happening very efficiently. And then you'd also want the energetic score to track with your mitochondrial or aerobic score. Your score tracks with it, but we would expect that mitochondrial score to be much higher. So what this suggests to me is that your energy balance is a little off. And so your fuel systems may not be optimized. And there's ways to do this, right? Cold plunging is a way to reset sort of fuel bases if you do it consistently. Intermittent fasting is a great way to change your fuel states and rebalance whether you're using glycolysis versus mitochondria. And a lot of this we think is tied to what's available, right? So your mitochondria will use anything. Your energy systems will use anything to survive. And so if you've got a lot of sugar, you'll use sugar. If you've got a lot of amino acids, ketones, fats, your body will somehow adapt to this. And so we want to look at that fuel flexibility. And so this suggests that there may be some elements where we could tweak this. This then goes back to that previous result we had where your baseline respiration was lower than normal. So it suggests that because of that lower than normal, that could be tracked to some of the inefficiencies we're seeing in how your fuels are being optimized and used, right? So one test sort of confirms the second phase. The final panel then goes on to looking at baseline and stressed reactive oxygen species. And so we have a fluorescent-based assay that we can look at. So we adopt your environment. We look to see how many free radicals are being generated. And then we do this in a stress setting where we make the mitochondria work as hard as they can to see if they're coupled or making ROS. So yours are doing quite well, right? Your baseline ROS is low. And when we stress the system, it's in the low and gets even better. So you have some resiliency built in. So I'm sure the product that you have has got a lot of antioxidant components to it. And if you take it routinely, it's doing what it's supposed to do. We see this mitigation of oxidant potential. The final thing we look at is mitochondrial network dynamics. So what we've done is we've created a cell that we're expressing a green protein in those cells. And so this green protein lights up all of your mitochondria. And so under a live fluorescent microscope, we can see how these green mitochondria are moving around. So when we add your environment onto this green sort of network gets animated, right? And we can look at this. And so your mitochondria don't sit there. They're not static. They're constantly moving, churning, dividing, fizzing, fusing. And so this network dynamic looks at that. Yours is on the higher end of average, suggesting that there may be some issues with the dynamic component. So mitochondria, just like we are social organisms. They like to be connected to each other. When they're connected to each other, they create resiliency because they can talk, right? So they share information, so they can buffer calcium, they can buffer ROS, they can buffer stress, they can do all of these things. If you look at every chronic, non-communicable chronic disease that exists, at the electron microscopy level, you look at the tissue endpoints and the mitochondria have become separated, right? They become separated from that network and they start to round and dysfunction. And this is what leads to a lot of these chronic disease processes that people are dealing with. So network becomes a huge component of stabilization of your mitochondrial energy. So that in a nutshell is what mescreen does, right? It looks at your stress response, your energy profile, and then ultimately is that stress and energy profile being flavored by the reactive oxygen species you're generating and how your network is behaving. So it gives you a real complete picture on who and what you are from an energetic perspective, and all off of a couple drops of blood.
Yeah, it's pretty impressive. Now you have a couple levels, right? I went for the full complete. Is it
That's one of the things we've been internally doing. We keep, I mean, this is so new, right? It just launched in December. So one of the things we figured out is that I think you're doing a disservice if you only do one panel, because you need all of that information to learn about the individual. And so we're eliminating the one panel thing. So we're only moving to a complete, and we've dropped price on it as well to make it affordable for everyone to do. I think that in terms of mitochondrial health, why sort of scrutinize and mince pieces, right? Just give everyone the full thing. And so we're really moving to this idea that you need all of this to know what your mitochondrial health is and to really move the needle into a healthy state.
And you're probably pulling the data just right, like so that you can add it to your AI as a data point, but just not presenting that because
so eventually when we're a successful business and we've got hundreds of thousands of data points in there, we're going to share this with people, right? So we will have unique markers that come out that peg you against different diseases, elite athletes, and you get to see where you sit against them. The other thing that we think we can get out of this in terms of longevity and other things is mitochondria are a conduit for living well and living long. And so we think that we may be able to eventually come up with an algorithm that predicts biological age based on your mitochondrial function. And I think this is going to blow the doors off of epigenetics because, this is how I think about the nucleus. It just sits there, right? And you're waiting for it to be manipulated in a unique way. Whereas your mitochondria are constantly moving, your energy is constantly moving. It's what's manipulating life. And so why not look at the dynamic aspect of biology as a way to predict your biological age versus the thing that's being dynamically manipulated, right? So that's where we're headed.
Yeah, no, I think that's it'd be really fascinating, and had I done a little bit more forethought into this, and even looking at my data, is like, do you have a stand? And I know your data set's continuing to grow, but if you could say like, hey, this is what we snagged 3 people who have a particular type of cancer. This is what they look like. Yeah, snagged 3 ultra elite athletes, and this is what they look like, and theoretically why. As we were kind of looking through my data, let me share what I tend to do. I'm high protein right now, but I don't think I was when I took this test.
Yeah.
I'm definitely low carb. And so maybe there's pretty low carb, but and then on weekends I do whatever. So food wise, I think I'm certainly not on the standard American diet. Like none of that's happening.
Yeah. And then fasting at all? Intermittent fasting?
I do fasting, right? And now I typically do a 24-hour fast. And at that time, I was at least doing, I think, 18 off, right? So last meal by 9 p.m., first meal at 3 p.m., which is really 6, but I call it 10 because I have a little snack, a little tiny bar of chocolate, which is the wall between me and a whole cheesecake. So in terms of diet, I'm doing intermittent fasting. I'm doing resistance training 2 times a week. I've backed off. I was doing kind of more aggressive cardio, and I really moved down to zone 2, just kind of fat burning cardio, which is hard. I played semi-professional soccer. It's hard to train zone 2? Like, I don't know what your kind of background is, but, and I've got a personal trainer and we talk about it all the time. If you want to just, train in zone 2, like, I feel like I'm Pee Wee Herman having a little bike ride going around town going, hey, everyone, right?
Yeah.
Like, it's just that slow. But that's what I've been focused on. I don't know if that makes sense given the data that we've just
It does.
seen.
I mean, you look pretty good on this mescreen test. I mean, there's things that could be tweaked, but nothing horrible. I mean, this is not a diagnostic, right? I'd love for it to be, and we're moving down this path where once we collect more and more data, we will go down the FDA route, right? We will be able to tell lots of things about different disease processes, and the company's already starting to sort of create the infrastructure to move this as a diagnostic test, which is going to be amazing. But right now, it really gives you a sense of your wellness state and where you sit. So from the read of this, I think you're doing the things that you need to do. Some things that you could consider would be a mitophagy activator, which will clear out sort of the dead dysfunctional mitochondria. And so there's products out there. Urolithin
Timeline,
A,
right?
Timeline. Yeah,
Mitopure.
Mitopure is an amazing product for that. They've done lots of cool studies around this. Resveratrol, you can drink a lot of red wine or take the pills. I'd rather drink.
I've opted for one of those.
French and Italian, I think, are my favorites.
Yeah.
But I think you'd have to drink a couple bottles a day, which I don't recommend, right? The balance between the alcohol and resveratrol. But there's, lots of ways to do this and different regimens. One of the things that we're very interested in tied to this is the blue zones, right? There's spots across the world where people live way longer and they live these extreme lifestyles from the standpoint of age, but they don't live extreme lifestyles from the standpoint of what we do.
Yeah.
And biohacking, I don't think has sort of caught on to this idea that maybe you don't have to overdo things. You just have to do things in a unique kind of way. So live in a hilly area and walk up and down hills, walk uphill both ways if you can.
Yeah.
And drink herbal tea every morning. There's some unique factors. The other thing that I think you can't replicate in this biohacking world is community, right? One of the things that I think is common across all of these blue zones is there's these intense relationships that form between individuals, whether they're friends, family, multi-generational homes. This gets back to what we were just talking about with mitochondria. They're communal organisms, and so are we. And so if we find a way to attach to other human beings, we create a lot of stress resiliency and all these other things, right? And so I think there's knowledge in there.
Because I have you, I get to pick your brain. I probably shared with you our current theory about our molecule, right? ESS60, the BOSS theory, buffering oxidative stress system.
Yeah.
We know that the molecule gets into the mitochondria. We believe that it can hold reactive oxygen species in those cases where it's overloaded, in those cases where we just get depleted. So maybe the glutathione and melatonin that are typically managing the reactive oxygen species after they're made is depleted. Then we're holding on to them. My director of research came to me and said, this also has another potential, which is if you're holding those charges, like what do those reactive oxygen species typically do when they're made? Do they pop out of the mitochondria and then start doing damage inside the cell?
Yeah.
Or do they stay resident?
They're reactive, right? So they don't really have a huge distance that they can travel. And it's almost a misnomer, right? People tend to fixate on the negatives all the time. So if you make a lot of free radicals in reactive oxygen species, reactive nitrogen species, there is a potential to create injury. But they also have a signaling role, right? I mean, the Nobel Prize for nitric oxide, right? Everyone was wearing these shirts called "What part of NO don't you understand?" Right? Came out. It is a signaling molecule, but it's also used as a molecule to kill things, right? Bacteria and other things. And so there is that signaling potential. So your mitochondria releasing small bursts of free radicals is a way to create resiliency and health. And so you don't want to completely shut down that process. You need to have that natural low level happen.
Would there be any potential, pun intended, value in holding on to these negative species, right? Because they would, in fact, like if they normally pop out or go out and burst, if they're being held locally, then they're creating a negative charge. And now you've got this negative charge across the membrane of the mitochondria. Do you see that as, hey, that could be problematic because of X? And we are talking about biological systems. So like.
Yeah. They're complicated, right? One of the things, in my work we did in my graduate studies where we were looking at heart protection, the concept that Nietzsche proposed in philosophy comes through, right? That which doesn't kill you makes you stronger. And
Yeah.
so this concept that poisons are actually kind of good if you take them in micro kinds of quantities. Anything you look at is a mitochondrial stressor, but if you take it in a small dose, it creates this huge resiliency phenotype. So my thesis actually focused on opioids, and so what we showed is that these really tiny doses of opioids release a small burst of free radicals that then ultimately lead to this amazingly adaptive protective potential in the heart. And it mimics what would happen when you do these mini micro heart attacks. It turns out that when you do these mini micro heart attacks, the heart releases a small amount of opioid, which then feeds back onto itself to cause this protected state. So there is that element there, right? So
Interesting. I
stressors
got
are
one more
good.
question, and then I want to get into our wrap-up question. So, as I'm kind of
Yeah.
forced to dig into mitochondria, understand it, right, because of the boss theory,
Yeah.
I'm popping around on the internet and really have come to I talk about every cell in your body has between 50 and 5,000 mitochondria in it, and that was a number I found, and I referenced it for quite some time, except for your blood cells, right? They don't have any, and then I find one that's like neurons and nerve cells actually have like 2 million mitochondria, which does not sound like the statement between 50 and 5,000, and then these have 2 million. Like this just feels like an uneducated lumping of stuff. And then on top of that, I was doing further research yesterday and found a couple of references to there's a lot of mitochondria in your retinal material, right? So in your cones and rods in your eyes, and great, makes perfect sense. But then I can't find like, well, how many? Like why does this seem? It seems like it's maybe hard to count, or like any ideas?
There are certain organs, so your brain for sure, things that use a lot of energy, right? Your brain's never really turns off. Even when you're sleeping, it's on.
Yeah.
So it's consuming energy all the time, so you need it. Your heart, if your heart turned off, you'd be dead, right? So it's constantly on for the whole lifetime. Your heart is 30% mitochondria in terms of volume, so it is a
Wow.
ton of mitochondria. Your kidneys have a ton of mitochondria, your liver have a ton of mitochondria, your eyes have a ton of mitochondria. So there's certain organs that have a lot of mitochondria. And one of the reasons why you need this is there is no battery in your body, right? Once you make ATP, you have to use it. There's no way to store it. For an example, in the heart, it has to basically make the energy, use it, make more, use it. So it constantly has to churn this, which is why you need the factory to make this stuff. And I think I've seen some numbers. I think you make multi kilograms of ATP a day, but your mass doesn't increase by that because it's basically consumed as soon as you make it, right?
Yeah.
And these are systems that need it. There are ways to estimate. We've done volume estimations from electron microscopy. So electron microscopy, you're looking at a tiny speck of a piece of a cell, and then you have to extrapolate out in terms of what volume and numbers that you see.
Yep.
And it just becomes astronomical, right? And so there's best guesses. The numbers I saw when I was looking this up, I think someone said, and I'm like, how did they count? They're saying there's 74 trillion mitochondria in our body, which to me makes like complete sense in terms of numbers. They're everywhere, right? It's the highway that connects every one of our cells except the red blood cells. But it's a large number that we have in our body.
It's just interesting that this seems like the fact that the data, like there should be one website was like, hey, this is how much is in your heart, liver, like, and you referenced some of that, and the fact that there's no kind of concise spot to pull that information means that it is still relatively new, right? Like that's kind of the implication, which is exciting. Like we're talking about whatever in its kind of most pedestrian terms, the powerhouse of every cell, which is insanely important. But then that doesn't even take into account the other implications. All right, so I have some wrap up questions for you. These can go rapid fire.
Yep.
Dr. Patel, do you have a target age that you want to live to?
I don't. I think one of these things is I just want to live well. I don't know if I want to live for a really, really long time. I just want to be healthy as I'm living. And then just not sort of the goal. And I've been thinking about aging for a long time in our systems, and there is this narcissistic thing that certain people have that they want to live forever. I don't know what I would do with all that time, right?
I think I know what you would do, right? Because just digging into your past, like you're
Yeah,
digging into different areas. Like somebody's going to pop in your office and like you should, I don't know, you should study what happens to humans and their mitochondria when they go deep into the deep ocean. You're like,
yeah,
okay, like
yeah. No, so my answer to that would be I want to live well for a really long time, and when I'm
yeah,
not well, I don't know if that's a goal of mine is to live unwell, right?
yeah.
So
Well, and that's what happens, you know, when I talk about the research behind our product and a 90% extension of life, a lot of people, their first response is, why would I want to live longer? Because we don't separate living longer from living infirmed.
yeah.
And I get that. Now, different question. How long do you think humans can live?
So we've been thinking about this a lot as well, right? There's these old, I think they've been debunked, these hypotheses of aging, where one of the concepts that I think an Austrian has put forth is that you are born with a finite number of heartbeats, and and this is across organisms, once you consume those heartbeats, that's it. You can't do anything beyond that. And so it literally falls on a linear line. So if a mouse heart beats 700 beats a minute, their lifespan is about 2 years, right? And elephants have a slower heart rate and they live longer. Humans are the only things on this curve that don't fit on that line. They move off of this line. So we started to do things that extend it in unique kinds of ways. And so one of the concepts we've had in the lab is the pet protein that my lab works on is called caveolin, and we have a large group that works on this protein. It's a membrane marker protein that creates these complex sort of spots in the membrane where lots of signaling molecules end up. So we think that it's an efficiency molecule, right? And so for the heart and the brain, it becomes this conduit for creating efficiency and resiliency. We have lots of data that shows that if you express this in the heart, specifically in animals, they live way longer than they should. The first death we see in a mouse naturally happens at 27 months with this protein only in the heart. Whereas the first natural death you would see in a wild type non-overexpressed animal is at 18 months. So by just tweaking one protein, we've extended lifespan almost 10 months, which is comparable to 3 or 4 decades in a human.
Yeah.
And then the other part of the group, my good friend Brian Head runs this division, is looking at this protein in the brain, which is where the therapies with ALS and other things come in. And so we've had this running joke is what makes you live longer, your brain or your heart? Ultimately, it turns out it's the pump. You need the pump, right? You need the blood to go to the brain and all these things. So in this animal where we've tweaked this one protein, I think we can get comparable to about 130, 150-year-old human, right? I think that is probably the natural capacity to age if you don't do crazy things to undermine that. Smoking, drinking, other things. But then you start looking at these blue zones, and maybe smoking, drinking is not a bad thing.
Maybe it's a good thing.
So there's an element to that. But I think having a good heart is probably a key feature to living longer.
Even when the first data started coming out about, hey, drink, a glass of wine is good, I'm like, yeah, and this may even have been, 10, 15 years ago. In my mind, I'm like, yeah, I'm pretty sure that's corollary, not causal, right? In that the person who carves out the one drink a night actually has really done a good job of segmenting stress, right? And so this is the time to de-stress. And if it's with a glass of wine.
And I think you got to look at when you're drinking that wine. I mean, are you drinking alone or are you drinking in a group? And maybe you're seeing that effect because you're drinking socially with other people. And it has nothing to do with the wine, just the social interactions possibly.
Exactly. All right. Next question. What are 2 to 3 protocols, habits, mindsets? Let's call them shortcuts because everybody likes shortcuts to longevity and a long health span that you would share?
I think one of the things working with Joe over the last couple of years, I think meditation is a key feature of this. I wish I could do more of it, but incorporating that into your daily lifestyle, I feel amazing when I meditate. And it's like my brain hasn't learned this yet, right? So why don't I just do it every day, all day long?
Stupid brain.
If I could, I would love to do that. But I think a regimented, focused practice of meditation is a good thing. And I think we have some data in Joe's world that suggests that this is a great way to protect the mind and the body from the ravages of age. We're eventually going to look at biological age, but everything points in that direction, that if you're meditating, you're living way better, more resilient, and potentially aging at a much slower rate. People have talked about, I mean, when I first started this work with Joe 4 years ago, I looked probably 30 years older than I do now. I'm maybe I don't, whatever I look now, but I've looked like I'm a younger person, right?
Yeah.
And there's an element to this with stress and meditation and adaptation. The other aspect that I struggle with, that I think people struggle with all over the world, is sleep. If you can sleep more, I think this is a regenerative process. Our bodies need rest. Our mind needs to shut down for a focused period of time where it's not constantly bombarded by things. And meditation goes along with this. I think one of the things that meditation makes you do is shut your eyes when they're normally not shut. Sometimes I'll turn the lights off in my office and close my eyes. If I'm having a rough day, this is a complete way to reset everything.
Yeah.
So I think it really goes around this idea of how to reset. And this is something that I think we as humans have forgotten how to do. So those are the two things that I would recommend: sleep and meditate.
Excellent. And Dr. Patel, how can people contact you?
If you look me up at Hemal Patel, UCSD, my email pops up, and that's the best way to contact me. I can't guarantee that I'll respond right away. I get thousands of emails, but I will, if it piques my interest, I will respond.
Excellent. And they can also find the test that we went over.
Yeah, so you can go to mescreen.com. So this is run out of the university, so it's a separate company that runs this, that I'm the chief scientific officer for. And you can go to mescreen.com, and then we are coming up with a portal that people will be able to order tests off of soon as well.
Excellent. And if they send an email, they can probably finagle a test out of somebody if they
easily. I can connect them with someone who can get them a test.
And are you going, do you have a plan to go into any conference soon? I met you at the Biohackers Expo. Are you guys going?
The plan is to be at the Dave Asprey Biohacker Conference, the 10th annual one, right? That they're running.
I think that's right. Yeah. It's in the last week of May in Dallas. We're going to have a booth there.
Yeah. So we'll see each other in Dallas then. Yeah. So the plan is to be in Dallas at Dave's event and really try to make a huge mark in moving this test forward there. Excellent.
And what in the near future are you excited about?
Lots of things. I mean, we're really moving down this mitochondrial path. I think there's a way to really think about this in perspectives that we haven't been. mescreen is just the sort of the tip of that sphere that we're looking at. There's so many things under mescreen that just excite me. We have ways to get to personalized medicine. At the end of the day, is I think in about, I can do it right now in the lab, but at scale, in about 6 months, we'll be able to screen compounds for people and tell you what you should try, rather than you ever having to put anything in your mouth and see what's going to work for your biology, right? And that excites me, the fact that we can get to that level of precision without someone having to waste 2 years of their life trying to figure out what's going to work for them. We can do it in a dish.
That's phenomenal. All right, so you can reach him, Hemal Patel. I Googled him in kind of doing my research, and he comes up pretty quickly, so you'll find him. And then mescreen.com is the website where you can find the test and kind of stay up to date. If you're not going to the event in May, then you should go. There's a lot of amazing things going on there. Dr. Patel, thank you so much for joining us today.
Yeah, it was great talking to you.
I hope you enjoyed this episode of the Live Beyond the Norms podcast. Make sure to subscribe and follow. Also, make sure not to be that guy, the guy sharing this podcast with people who are not interested in living beyond the norms. If you would like to learn more about the ESS60 molecule, the molecule responsible for the single longest longevity experimental result on mammals in history, a full 90% extension of life, visit myvitalc.com. That's myvitalc as in carbon.com.